Everybody's probably getting food, so you're all making me a little bit nervous here. I have to apologize for my voice. I got a little bit of a head cold today, so just bear with me. So my name is Aaron. I'm going to be talking about optimizing our game, Race of Sun. So I'm the programmer for a little company called FlipFly. We're from Madison, Wisconsin. I have my contact info there if you'd like to connect with me afterwards. And Race of Sun is basically an endless 3D endless racer. Visuals were sort of inspired by Star Fox and games like that. We developed it for PC, Mac, and Linux first, launched on Steam, and then we came out on PlayStation about a year ago, so PS4, PS3, and Vita. And so the world is a combination of like hand-designed patterns and randomness, so it'll just keep going as long as you don't crash into anything. There's just a higher res screenshot of the game. Actually, I'm kind of curious how many people have heard of our game before they came to the talk. So, wow, that's pretty awesome. So, I just had to know. So, as you see here, each pattern is populated with designed objects. And then in each object in the game, we call it an object or a spawnable, is a combination of primitives, which are Unity objects. And then the patterns in the game, like I said before, are arranged randomly. And so at any given time, there's 9 of these patterns in the game that are just kind of generated right out in front of you. And they just keep going endlessly in every direction. So you go left, right, and towards the sun. So that's a little bit about the game, and I just want to talk about kind of the unique challenges that we had with Race of Sun, probably apply to other types of endless racer or endless runner type games as well. So the one big thing is that there's going to be lots of object churn. So lots of objects are just created in the game and then have a very short life cycle and disappear right away. There's no static world in the game to speak of, so everything is generated on the fly, and there's no one location that you're going to be in. Everything's created with basic primitives, so we have 4 different primitive types, just simple sphere-like objects, cubes, logs, and pyramids. And so as a consequence, there's lots of game objects in a scene at any given time. Even though the game looks pretty simple, there's actually quite a few objects. There's real-time lighting and shadows on everything. And it really needed 60 frames a second in order to feel good. 30 frames a second just really didn't cut it. And just due to the nature of the game, if there's any hitches at all that happen during gameplay, it would likely cause you to crash and just totally ruin the experience. So optimization was really important for a game. And so I like to think of optimization as like there's basically 4 classes of problems that you have to deal with. The one is spikes, and this is a big issue for Race of Sun or any type of Twitch game. If you get a 100 millisecond spike in your CPU one frame, you're really going to feel that. Every frame costs are just the little things that you're doing all the time that are just eating away that CPU or GPU time and slowing down your overall frame rate. Garbage collection spikes, which are they feel the same as a big CPU spike, but it's really a class of its own as far as optimization because something else will cause it. And then lastly, loading time. And so I'm going to talk a little bit about just kind of the optimization principles that I think we learned during this game that I think will apply to any game, and just how to approach optimization a little bit. And then the second part of the talk, I'm going to deal with what we actually did with Race of Sun and how I think it helped us. So the first principle is that every game is different. I see a lot of people on the Unity forums just jumping in and saying, my frame rate's bad, what do I do? And other people are jumping in and saying, well, I did this. And it's like, okay, I'll try that. And I think that's kind of a bad way to approach optimization because every game is going to have its own challenges. Don't assume that a bottleneck in one platform is going to affect another one. And don't assume that a solution on one platform is going to fix something on a different platform. Every CPU and GPU is different, so you really kind of have to treat each platform as its own thing. Of course, some optimizations will cross over, but I guess the point is don't optimize for the iPhone and assume that's going to help you on PS3 or something. And the second principle is to use the profiler. This is the other thing that I see people doing a lot is just, you wrote the code and you know that this function you wrote was really crappy because it was just temporary and you're sure that that's going to, be a big problem. And so a lot of people will jump in and just like, I'm going to fix this because I know that's going to be a thing. And I think that's a bad idea. So really just make a habit of using the profiler from the beginning and do it on the device as well. We use various plugins, and some of them have editor-only code. So NGUI is our UI, for instance, and there were big spikes that we were seeing while we were in the editor, and I started optimizing and profiling that. And it's like, wait a second, that's editor-only code. So really get it on the device and go through the work to actually set that up. You also want to kind of figure out pretty early on whether your per frame costs are making you GPU bound or CPU bound, because that's really going to kind of change where you're directing your optimization efforts. For Race of Sun, there weren't a lot of fancy shaders and stuff like that. It was pretty basic diffuse shaders on most things. The lighting was pretty simple, and so most of our optimization efforts were on CPU. And the third principle is to prioritize. It's when you're working on your game for hours on end and you see something that's just like, this is going to help your game, it's tempting to jump in and just start optimizing something and refactoring your code. But really, you have to take a step back and think about how long it's going to take you to actually make that change and what is the effect going to be on the game? What is the actual win? So you got to do a little bit of a cost-benefit analysis, and you have to think about the potential side effects of the change as well. This happened a few times with Race of Sun, where I would dive into a change to optimize something, and it might take me a day to make the change, and then I'd spend the next 3 days like fixing all the little things that broke because of that. And so you really have to just think about, what's the lowest hanging fruit. So I always recommend starting with quality settings. You can change the shadow distance, the light quality, things like that. Those things can make a pretty huge effect on your game, and you kind of want to set those to what you need them to be first. Trivial refactoring. Sometimes there's things that you're doing in your code that are just really easy to change. You can change a for each loop to a for loop, and I'll get into that later. And that can be a win if you're doing it a lot. Things that won't have big side effects. Try swapping out your image effects or turning them off and see what the effect is. So you've got a really fancy bloom shader, with high quality settings or something like that. It's pretty easy just to tick that thing off and then measure the change. And the fourth principle is to measure the effects of your changes. And so this is the other thing that's tempting to do, is just to jump in and start optimizing like crazy, and maybe you measure it really casually and move on to the next thing. I think it's really good to actually pay attention to what's happening with your changes. Get out a pad of paper and write down like how much time did I spend in the rendering call every frame, before this change, and then make the change. Go in there and measure. It takes a little bit of time, but you can say, for sure when you're done, like, I made this change and I saved 3 milliseconds on the rendering thread, and so this change is probably worth it. Sometimes you have to weigh, I'm going to make this change and it's going to cost something else, or it's going to take some time to implement properly. So you want to know whether it's worth it or not. And if you can, try to recreate the gameplay between sessions when you're doing that measurement. So, if you're developing an action game and one scene has 10 guys in it, and then you play it again and there's 15 guys the next time, it's going to be really hard to compare the frame rate. So if you have some mechanism for recording demos and playing them back, or something that you can make play through the same sequence and then measure those frames between one run and the next, that's going to be really helpful for you. And make use of the profiler begin sample and end sample functions. Those are basically a way of measuring a slice of code, but be aware that there's an overhead to that. And so if you've got some function that you're calling 50 times in a frame or 100 times in a frame, just be aware that when you're adding those profiler things, you're actually adding to the overhead of that as well. And if you're doing that recursively or something, then you could be digging yourself into a hole, and you sit there optimizing for hours, and then eventually you realize that you're actually causing it by trying to profile it. So there's a little bit of a problem there where you have to work around that. try to profile things on a high level. Use the profile begin sample, end sample to, get an idea where you're going, but then, measure it at a high level. And sometimes you're trading loading time for per frame cost, and you just have to make some hard decisions about, do you want to add 3 seconds to your load time in exchange for optimizing something ahead of time? Principle number 5 is what I call beware of death spirals. And this is kind of a per game thing. It might not affect you, but the basic idea is that sometimes you're doing something where if you spend a lot of time processing something on one frame, you're basically creating more work for yourself the next frame. And so with Race the Sun, you can imagine that you're flying into the world and you've got all these objects coming at you. If you spend a lot of time on one frame because you're spawning something, that frame, your player ship is going to go farther. And so that as a consequence, you're going to be spawning more objects as you go farther in the world, and that kind of creates a death cycle where you're just spending more and more time doing that. And so with Race the Sun, as I optimized things so each frame was not spending a lot of time processing stuff, the distance that you went each frame was minimized, and that just kind of created less work. And so it's like you're either creating an upward cycle or a downward cycle. And so small changes can have big effects sometimes, in a good way or a bad way. And then principle number 6 is just to step through your code. And this is something I think is a good idea, regardless, but every once in a while just get out the debugger and step through everything that happens in a frame. You're probably going to be surprised at some of the work that you're doing. And for me, there was lots of code that I wrote like a year before that I just totally forgot I was doing, and it's like, oh, I'm checking for objects for the whiz-by sound, and I really don't need to be doing that every frame, So just every once in a while, make a point of stepping through your code, and you'll probably find some things that are really easy to clean up. Obviously, the best way to optimize a chunk of code is to not run it at all. So this will kind of facilitate that. So that's it for the kind of general principles that I hope will help you with your game. I'm just going to talk about Race the Sun optimizations and kind of what I did here. I can't guarantee that this will help with your project, but if you're making a clone of Race the Sun, it probably will. So the first thing, and this is probably something everybody knows about, but create object pools for things. Don't instantiate things at runtime all the time. And you'll probably run into this really quickly if you're making a mobile game anyway. If you instantiate a complex object from a prefab, it's going to cost you a lot. And so just don't do that. That'll save on your per frame costs, and it's going to create less churn for the garbage collector as well. And so the second one was probably the biggest win outside of the object pooling. And so initially, like I said, all these objects were created as a collection of primitives makes up an object, and then a collection of objects makes up a pattern, and then 9 patterns makes up the world. Initially, every one of those primitives was an individual game object, and that was just not going to fly on mobile platforms at all. We had hundreds of dynamic game objects that were all individually lit, casting shadows and stuff like that, and there was just too much overhead with rendering and physics and all that stuff. And so basically what we did is we wrote a script that would, at load time, it would combine everything that didn't move in an object into a single object. And so if we had a moving car and it had a few different primitives on it, it would kind of glue those all together into a single object. And then we use that as a rendering mesh and the physics mesh. And so that reduced the object counts pretty drastically. You can see in this screenshot I have here, so everything that is in that scene other than the blue power-ups is kind of merged into one pattern object. Unfortunately, that processing time at startup added about 25 seconds to the loading time for a level, which put us at something like 40 seconds for a level load. So I'm going to talk about that later. Actually, I'm going to talk about that right now. So optimizing those objects at level load took way too long. And so what we did is we wrote a a custom editor script that we would run on our scene definition file, which was just an XML file. And we would save those prefabs, or save those patterns as a prefab, basically, and put that into a baked level. And then at runtime, we would just load that level up. And so these objects, which were defined in an XML file and a custom level editor, were kind of saved into a scene file that were just set aside. And so that reduced loading time significantly. So it went from about 45 seconds down to about 15 seconds on Vita. And this is in Unity 4.6 as well. So I think our loading time is actually quite a bit lower on 5. It did add a few megabytes to the disk size, but we're well under 200 megabytes, so that wasn't a big concern for us. And then at this point, we had fairly smooth per frame cost. We'd gotten rid of a lot of the little stuff. However, there were issues like when you cross the boundary between patterns and we had to spawn in an entire pattern worth of objects. Sometimes there were a lot of those moving objects, and we'd be, I say spawning, but really it's just kind of like taking things out of the recycled pool of objects and putting them in the world. That would incur a small cost, and when you do it 20 times in a frame, it added up to maybe a 30 or 40 millisecond spike sometimes. And so the solution there was just to defer the processing of those and do it over a few frames. And so you just make a list of objects. These are the objects that you're trying to place in the world, and coroutines are a big help here. It makes it really easy just to say, take this loop of things and put it in a coroutine and then just put a one frame wait in there. And it was pretty simple. I didn't try to get too fancy with it. Basically, do a few, whatever the task is per frame, and I just kind of measured it and saw how well it worked and moved on. And so that helped avoid the big spikes that would happen occasionally, and just helped things smooth things out a lot. And then the other big thing that we had to take care of was the garbage collection spikes. So how many of you have had to deal with like big garbage collection spikes in your game? It seems like a pretty common thing with any engine that has garbage collections. So, and it was really a big problem with Race of Sun because, as I said before, if there's a big spike, then you pretty much die and you hate the game and you never play it again. So we had to take care of that. So this actually took a pretty big chunk of my time. Like I said before, we developed Race of Sun on PC, and so there were a lot of things that I did that were just kind of really not optimal at all. If we had been testing on mobile devices the whole time, I probably would have been a lot more aware of little things I was doing, like adding strings together. Coroutines have a little bit of overhead, and the way that I set up the code for spawning the world used coroutines quite a bit, and so we might have like 30 or 40 coroutines on different processes that were spawning objects in the world, and there's a few bytes that were allocated each time. And so as a consequence, we were just churning through a lot of memory, and there was no choice but to do garbage collection during gameplay. And so there's just a lot of little things that I had to do, caching the results of Git components and children, cleaning up string additions and stuff like that to not allocate memory as much at runtime. And so I do force a garbage collection right after the level loads initially, and then I force another one right at the end of a region. And so the game is split up into regions, for those of you who haven't played it. So you finish one region of gameplay, and then there's kind of some downtime between there, and that was kind of a good spot to call that. Sometimes you feel it a little bit, but it doesn't really affect the gameplay much, so we kind of got away with it. I also pre-allocated a chunk of memory at startup, which expands the heap, and it basically raises the bar for how much memory you have to allocate before the engine is going to force a garbage collection. And I've got that in a link here if anybody wants to snap a picture of that. And so basically we don't avoid garbage collection altogether, but we control it. And so it only happens when we want it to, and that just solves the problem for us. And then just lastly, there's a few miscellaneous things that I did. So the fixed time step is basically by default in a Unity project, I think 50 frames a second. And we could get away with lowering that a little bit. We don't have any rigid body physics in our game, so we didn't really need to be doing that very frequently. Only use fixed update for rigid body physics, by the way. At first, I had player movement happening in the fixed update function, and I think this was because of some Unity forum thread I read where somebody said to do that, and it was just a bad idea. So it's actually happens in the update function, and I use a character controller for the player ship. For the Vita at the time, turning off VSync seemed to help the frame rate. That was something that was recommended by a Unity person, and it helped just smooth things out. And again, just tinker with the quality settings. Try different image effects, try different settings in the image effects. The default bloom shader, it may have been optimized. This is Unity 4.6, but some of the image effects require different things like stencil buffers and stuff like that, and you don't always notice ahead of time, but that's going to incur some CPU cost, and sometimes it's pretty heavy. So we swapped out the bloom shader for the optimized bloom shader, and that basically just eliminated that problem, and it looked about the same. And then there's lots of little things that are just unexpected, and this is part of why using the profiler is so important. So, for a while there was something where having 2 cameras in the scene would make something happen with low-level rendering code that would end up costing like 30 milliseconds, and there was really nothing we could do about it, but just knowing it was there let us kind of try different things that solve the problem. Our object pooling system, when we disabled objects when they were recycled and then re-enabled them, that was incurring like some physics-related costs that were sometimes adding up to really big amounts. And so I had to do things like only disable the renderers, and that would save on the rendering thread without disabling the physics. And that was kind of like the right combination of changes that let us not have spikes, and the per frame cost was low as well. So there's a little bit of voodoo, black magic stuff in there, but be prepared to spend some time doing that. And then lastly, when we upgraded to Unity 5, that just magically fixed a lot of performance issues for us as well. So, that's definitely some advice I have if you're stuck on Unity 4 for whatever reason, and you're considering, am I going to have to update this plugin, or am I going to have to whatever? Like, if you're suffering from performance issues, I definitely recommend upgrading. And so the results, I spent probably two to 3 months optimizing, mostly for Vita. And those optimizations crossed over. Most of them helped us out a lot on iOS as well, so it made that port a lot easier. We did end up disabling dynamic shadows on Vita in Unity 4.6, which I was pretty disappointed about, just to make the game run really smoothly. And then when we upgraded to Unity 5 recently, it gave us back enough CPU time that we're going to re-enable those in a patch pretty soon here. So the game runs at 60 frames a second most of the time. Sometimes it dips down to 50, but we've pretty much eliminated all the spikes, and it runs pretty smoothly. And so yeah, I guess the overall result is that the game runs smoothly, and people really notice this. The game has been cloned a few times, and something that the reviewers have called out on the clones is that a lot of times they're really hitchy, and it just doesn't feel smooth like Race the Sun does, and some of that's kind of intangible, but it really comes back to this time that we spent optimizing it, and I think it's just really important to just spend your time making that experience great. Your players are going to really feel that. So that's about all I have for my talk. If anybody has any questions, I'd be happy to answer them.
Hi, thank you for the talk. Can you say some more about for each versus for and garbage collection? I noticed you had a note on that.
Sure. So it's just it's related to the mono engine. It might not be an issue with IL2CPP. Somebody from Unity could probably confirm that, but it still is. Okay. So basically, if you use a for each loop, it's going to incur a very small memory allocation. And so, it's probably not going to hurt you most of the time, but I wouldn't do it on something that is happening every frame in lots of different places, where if you use just a regular for loop, it doesn't have that problem.
The memory allocation based on the size of the thing that you're iterating over?
What's that?
Is the memory allocation based on the size of the thing you're iterating over?
I don't think so. I think it's more of a constant thing just for using that type of loop. It's also true for coroutines as well. So if you use any type of coroutine, any kind of real yield wait function, there's going to be a small overhead for that, and it's going to depend on the type. But even like a yield return null is going to cost something like 4 bytes. So
Okay, thank you.
the iterator itself, yeah.
So I had a similar, well, I had a lot of GC allocation, hitches in my game as well. And on a different level, one thing that was happening with me is so the game is like this 3D version of Snake, and every X position change will create a new edge loop in the mesh that's being created behind you. So like sometimes that's happening every frame. Sometimes that's happening like 3 or 4 frames in between, and I was trying to figure out if there was a way to, I'm doing it in a coroutine, but like kind of if I have to do something that finishes on frame 4, but I have 4 frames to do it. Did you think about things where like, I think it would be similar for you with generating your world, where you could do like half of a chunk, or like half a chunk per frame, because it's going to be 3 or 4 frames until you need to make the next chunk. Did you do any of that kind of stuff, or?
I think I know what you're saying. So it's kind of like you want to split it up over time, but it needs to be done by a certain time.
Exactly, yeah.
Yeah, so we did have that problem. Like, for instance, when you finish a region, the next region has to create new building pools for different types of objects. And so, there's probably 1,000 or a few thousand objects that we need to spawn there. And so I would process like 10 of them a frame or something like that, or maybe it was like 3 per frame.
So you just break up your set by number of frames?
I would just split it up. So it's just, I would put it in a for loop in a coroutine, and I would say, do 3 of these this frame and then yield.
Right.
But I'm kind of tracking where I'm at with that process as I go. And then if you get to the end where it's like you're starting the next region and you really just need to finish this,
Then it'll just do it
then I
all.
would have kind of a fail safe there where it
Right.
says like just stop the coroutine and like just process all these at once. And so,
Yeah.
and that's one of those situations where doing that adds a lot to the complexity of your code. And there are a lot of cases with Race of Sun where I wrote some fancy system like that, and it added a bunch of bugs that I didn't catch right away. And so I'd spend like the next week just fixing all this
Or
crap that I broke.
You make it slower anyway. Like
Yeah.
the check is slower than just doing it all.
Right.
Yeah.
Yeah, and sometimes splitting it up into 1 object per frame or something just isn't enough. Like sometimes spawning this object with a complex collider on it is going to create a static collider, and there's just like that costs like 50 milliseconds on mobile, and you just can't get away with that. And so you need to kind of pursue other solutions anyway. And so always do like, if there's something that you're thinking of doing and it's going to be a really complex change, like try to think if there's a way you can kind of hack the change in without actually getting all the way. So if you can spend an hour like hacking that change in and measuring the difference, then like, okay, now I'm going to commit this 3 days to actually do this properly because I know that it's going to give me this.
Right.
And there's kind of there's a learning experience there that you get better at with time. So.
And when you mentioned concatenating strings, for me the secret was a string builder. Is that the case for you?
We use string builder. Yeah,
Yeah.
I use a string builder
Cool.
as well. Yeah.
Yeah, you didn't mention that explicitly, so I just wanted to bring it up.
Yeah, that's a good point. So string builder is a way to kind of add strings together without allocating as much memory. I think it still allocates a little bit when you create the string builder, but it's not gonna.
If you generate it with a buffer that's big enough to fit, like here's a 10,000 character string buffer or string
Right.
builder, it will only allocate like a linked list, right, when it needs to grow its internal.
Right. Yep. Yeah. So string builder is a good tool to use.
So you were mentioning that also coroutines and every yield in a coroutine also causes memory allocation, and that you had a huge refactoring pain because of that.
Yeah.
You were mentioning that you had like 30 or 40 coroutines running, and that already caused the problem? Because I thought like 30 coroutines and yielding on that wouldn't cost that much memory allocation. In a for each loop, if you do that in the onUpdate method and have a lot of number of objects in that list, then it would be a problem. But already for 30 coroutines, I never had that problem. So I was wondering what you did
Sure.
there actually, and how you solved it.
So I had some kind of sloppy code that was basically running a coroutine on every object in the scene. and it was waiting for the player to pass by it so it could play this whiz by sound, which kind of sounded cool. And so as a result, like I had probably 30 to 100 at any given time coroutines running on these things, and since the game is running at 60 frames a second, I was doing a yield return null, which is basically a 1 frame yield, and so that's, every time you do that, you're allocating like 4 bytes of memory or something, and that times 60 times a second times 50 objects adds up to, like a few kilobytes a frame or something like that. And for us, that added up. It was adding up to enough that the garbage collector was having to do some work every 30 seconds or so. And so that was just, there were lots of little things like that where it's like death by 1,000 paper cuts, where you may get away with it, and it might not be worth trying to eliminate, your lots of usage of coroutines. But it's the type of thing where if there's an easy change you can make to avoid doing that every frame, then it's probably worth it.
Yeah, but then it were coroutines that were running the whole time, and not only like loading or setup coroutines.
I'm not sure I follow you there.
Yeah, so you were mentioning, okay, that were coroutines that were running and would then emit a sound or do something when the player has passed it. So you were having a while true loop probably in that coroutine.
It doesn't really matter what you're doing in the coroutine. It's more about just the yield function itself is going to allocate the memory. And so anytime you can avoid just having that yield statement be hit, and every time, if you say like yield return 1 second and you're doing that in a loop, every second you're going to be hit with that small memory allocation. So does that answer your question?
Yeah.
Okay, thanks.
You were mentioning that you're combining objects into a block
Yeah.
and then using the mesh collider.
Yeah.
Is that not more of a performance hit than keeping them separate and using box colliders?
You would think so. Part of the challenge with it is that because we built this awesome in-game level editor that let people let my brother, our level designer, combine objects and then scale them, and you could kind of combine them in a way where it would end up doing like a shear and stuff like that.
Oh.
And so we couldn't get away with the box colliders, and so I didn't really have a choice but to do that. I was prepared to do something where I was splitting up the mesh colliders into smaller chunks and kind of like enabling them closer to you and stuff like that. It turns out that the non-convex mesh colliders seem to work okay. There's essentially only one type of collision that can happen in the world, and that's between the one player capsule and everything else. And so if we had like lots of rigid bodies and stuff, that would probably be a really big problem. But for our particular game, we didn't actually really experience any issues with that. You're also moving a really small different distance each frame as a player, and so it's essentially you're testing the player versus whatever's closest to you. So this is where the profiler tells the truth. It's a good example of just kind of like you know that using a giant non-convex mesh collider with hundreds of polygons in it is going to be a problem, but it actually didn't hurt us that badly when we profiled it. So.
Awesome, thank you.
All right, thank you.